Hello guys, good morning from here at GMAT 41, and I am welcoming you to our live section on physics practical as you have showing on your screen. We'll be dealing with this practical physics. This is with respect to physics 108 that some students will be running in Unizik. However, even though I refer to Unizik, it's important for us all to know that wherever we are connecting to this class from, as long as we are doing works related to current electricity, we might be exposed to a practical work as this. So once again, welcome. Once you join this class, do me a favor, share the link to your friends. Okay, share the link to your friends so they can also join. A moment so that I can share the link to GMAT 41's WhatsApp group so that the friends can join, those that are available and free now. So just a moment. All right. Like I said, once you join, please share the link to this live section to your friends. Now, what we want to do right away is to see how we connect the circuit of your experiment E6. All right, because you should know how to connect the circuit, after which you talk about the readings. Have to take readings. So let us quickly do this. I've already practiced this with GMAT 41 students in our physical tutorial class. So we already have readings to read. But at least having it demonstrated one or two of the value is sufficient to guide you, after which we'll move on straight to see what we need to do regarding the graphical work. However, I think at this point, for every one of us that has been showing determination and are so serious with their work, plotting of graph shouldn't be your problem as at this moment again. And also, you know that it's the values you get in your laboratory work that you are meant to use. Whatever we get here, don't go copying this value anyhow to use. Please take note. I never encourage that. This is just serving as a guide. All right, so let us get to business. The first thing is to look at the instruction given to us. You have the instruction, and the instruction follows this diagram. I will show you this diagram. Look at it. Okay, so you have this diagram. I have it here on my device. I'll be making use of it, just showing you. The experiment follows this diagram you have there. So this is a standard resistor. This is a variable resistor. You know, you're going to be provided with a resistance box. Yeah. So this is the key, this is the ammeter, this is the cell, the source of EMF. You observe that you are expected to measure and record the EMF of your cell. Most cases, 2 batteries are being used. In most cases, that does not mean that it must be 2 cells, right? That you will be presented with in your laboratory. But previous experience shows that cell of 2 cells, each of 1.5 EMF is usually being used. But the truth is, if you measure the EMF as you are required to measure in the instruction, because the instruction in that experiment is 6. I think the first instruction said you should measure and record the electromotive force of the battery, the cell provided. So we are going to measure it, but please, there is a challenge. This live experiment, I could have kicked it off since, but I found out that my voltmeter, has a problem. This particular cap we are supposed to use, it has a problem. It got damaged. I think from the last time, there about 2-3 weeks ago, that I demonstrated a live practical of it with my students in our physical tutorial. So it got damaged, and for that reason, it will be difficult for us to measure the electromotive force of this cell directly as it is. But there is something I want us to do. Already, I have a lecture video that deals with, this concept where I measure the electromotive force of a cell. I think that was based on experiment E2 for last set also. Yeah, experiment E2. So the video lecture or the lecture video is available. Chinas, you're welcome. Emmanuel, Ezeagu, you're welcome. So measuring electromotive force of a cell shouldn't be a problem anymore. I've done something here. This is the voltmeter. Okay. Now this is our battery. You can see these are two cells, right? This is one of the cell. This is the second cell. So two of them, right? You can see that. Joined. It's either you are given a battery casing in the laboratory. I don't have a battery casing here. In either case, no problem. We are going to walk around what we have. Okay, Emmanuel, good morning. You're welcome to join the class. So the two batteries are connected with your masking tape. Now, this end of the battery, I think, is positive end. You can see it's positive. Then the down part, you can see this, negative. Generally, the part of your battery that has this cap, look at it, that has this, is positive, while the other end of it, that is flat, is negative. Look at it. So two of these guys connected. Each of them is 1.5 volt EMF. It's usually written on it. I think the part I sellotaped, yeah, it's usually written on it. You can see it, good. You can see 1.5 volts. So this 1.5 volts, this 1.5 volts. Two of them are connected in series. If you look at your cell, is it your cell or your circuit? Look at your circuit. You find out that the two guys are connected in series. And that is what I have here, series connection. It could be in parallel, but anyway, this experiment, it was not given in parallel, so we'll go straight with what we expected to do. Okay? I thank God that this particular experiment, what we are measuring through is the current. So using ammeter, the ammeter is intact. May God's name be praised. So this morning I discovered the fault with this 3 volt side, because normally to measure the electromotive force of this cell, we are supposed to connect. Look at this black cap. This black cap. Okay, this black cap is negative end, negative terminal of the voltmeter. You can see it written. Then these 2 red caps are positive terminals. If maybe I want to measure cell of EMF 1 volt rather. If I want to measure cell of EMF 1 volt, unfortunately, each of these batteries is more than 1 volt. Like I said, each of them is 1.5. That is why I am pretty sure that you'll be given 2 cells instead of 1 cell, because there is no 1 cell that is 1 volt electromotive force. Since this voltmeter, like the upper scale, look at the upper scale. The upper scale of the voltmeter measures up to 1.0 volts. And you achieve that by connecting one of the wires to this cap of 1 volt. You can see it written 1 volt. 1. Then, look at this guy. This one that is spoiled, I said, is 3 volts. Like for this cell now, these 2 cells are supposed to measure up to 3 volts, which means that this wire is meant to be connected to this cap. So take note of this, because I am pretty sure if you are presented with 2 cells and you are given this voltmeter, your wire is meant to be connected to this one that is reading 3 volts, not this one. Take note. But unfortunately, this cap is no longer working. Look at it. It's dancing, dangling. It has spoiled. So what I want us to do is just to show you how you quickly check your EMF. I'm going to connect this wire to this cap, which is meant to measure 1 volt. This guy is already far more than 1 volt. So if I do the connection, see the needle of this voltmeter is going to move and even cross these 3 volts, because the terminal to which I'm connecting the wire can only measure 1 volt. It's the upper scale. Since these two cells greater than 1 volt, the needle will go past it. Don't be scared. Don't panic. In your laboratory, you'll be presented with a good voltmeter. I'm sorry, my voltmeter used to be good. It just got spoiled recently, like I said, after making use of it in the physical tutorial class. So watch what you are meant to do. Let us assume that this is my 3 volt cap. You are meant to connect your wire. Your wire will go this way. All right. Then you screw. You screw. You screw. I want you to observe something, what I did. I turned the wire this way. The wire, I moved it this way, this way, this way. Because the cap screws this way. I already explained this concept in Experiment 2. You can watch that video to see or learn how these things are being connected, please, so that we can maximize our time. So having connected this, like I said, this is negative terminal of the voltmeter. So the wire from that, I'll connect it to this positive terminal rather. The red cap, they are positive terminal. So this one is positive, this one is positive, then the black is negative. So this guy, the wire from this negative terminal, I will connect it to the negative terminal of this cell. And I told you, you can see the negative end of the cell. Look at it, the negative end of the cell, which is this button. So the wire from there will go that way. Look at it. I've connected it. Then this wire coming from the positive end, this cap, the black cap, is will be connected to the positive end of this cell. Let's see. You can see the positive end of the cell. Look at it. This cap. So watch what is going to happen as I connect it. The needle of the voltmeter will move. Are you seeing it? It's trying to move now. Okay. So let's see. Positive end. Let's see. This is positive. The red cap is positive. So it's meant to be connected to this point. No wonder the voltmeter had gone the other way around. Gosh. Reverse it. Positive to positive, negative to negative. That's how the connection is being done. Think there's a problem with this voltmeter. This is terrible. Why now? Why now? If there's a problem, sorry, we are going to assume. I'll tell you what we obtained when I ran this thing live. Okay, and that was 2.9 volts. That was 2.9 volts. This thing has damaged completely. That's damaged completely. What is happening? This thing shouldn't cause me problem this morning. All right, did that come back? Something happened. I wrongly placed the terminals, so the needle went where it was not supposed to go to. So once again, let's go. This wire, I'm tying it to the negative terminal, the black cap. Just follow along. I just want to show you how to do the connection. But first, measurement of the electromotive force. But if you have been following our classes, how to measure electromotive force, you know, I've already explained that. Okay, so the second wire, see how I'm trying to fix it so that as I screw, I will not be screwing against the direction of the wire. You can see the screw is going this way. So we go. Good. And like I said, from positive terminal of the voltmeter to positive terminal of the battery. Look at positive terminal of the battery. This point. So this wire from the positive end we go here. Then negative terminal of the voltmeter to negative terminal of the battery. And this is the negative terminal of the battery I had showed you before. You can see it negative. Let's say negative terminal. So this wire will go there. Now watch what the voltmeter is going to do. The voltmeter is not moving. Does it mean that all this they are damaged? But I test run this and this one peaked. If it doesn't work, I'll go straight to the circuit, please. This is just so sad that this morning I'm just noticing the fact that the voltmeter got damaged. The voltmeter is meant to read this way. It's meant to read this way. Please, that's what you're going to see. Sorry about that. Sorry about that. You see, that's why you guys need to support this platform. So I would be getting or replacing this equipment. All right. Please, based on what I've explained, and I've told you when we ran this experiment the first time, the electromotive force gave us 2.9 volts. You won't get 3 volts exactly. You won't. So you record 2.9 volts. The reason why you cannot get 3 volts exactly is because of the lost voltage of this cell. So I have shown you how you would measure your EMF of the cell, and I told you it is positive terminal to positive terminal. That is positive of the voltmeter to positive of the battery, and then negative of the voltmeter to negative of the battery. I'm still trying to see what happens. It's a good thing that in this experiment, it's not the voltage that you are reading, unlike experiment E2. It's not the voltage. All these things are shaking already. Know why this thing just happened this morning. I'll replace it anyway. I'll replace it, but it's not today. All right, positive to positive. Let me still try it for the last time. If it doesn't work, we'll move on straight to the main connection. It's current that you are meant to read. Okay. I think the voltmeter actually has damaged, and that just happened this morning. It happened. There was a failure somewhere. You saw the needle moved. Let's move on straight, please, to the main connection of the cell, of the circuit rather. What has happened has happened. This negative has started shaking also. So I think I'm going to pull off this. Like I said, good enough. It's not voltage that we are reading. I'm taking this off. So we move on straight to the circuit. Now watch the circuit. Let me explain quickly. This is a standard resistor given. I don't know the possibility of their providing this for you. I don't know the possibility. They might run it straight. Now this is your battery. The battery is connected to the ammeter. And like I said, negative to negative. This is the negative end of the battery. You know, the shorter line represents the negative, while the longer one represents positive. So let me just show you. This is negative of the battery. This is positive of the battery. Okay? From your physics 102, you should be used to that already, under current electricity. So the negative end of the wire of this cell, this battery will be connected to the negative of the ammeter. So from here, negative to negative, which means that here will now be positive of the ammeter. From the positive of the ammeter, you run it straight to the key. Key does not have positive or negative. Take note. And this is our key. This is our key. This is our key, okay? The tapping key. All right. Then from there, you run another wire, which is going to be wire what? This is the first wire, second wire, and then third wire. Good. The third wire will be run into the variable resistor. Now we are going to be making use of these resistors. You'll be given resistance box, like I said. But I am going to be making use of each of these single standard resistors. All right, be making use of each of these single standard resistors. This resistor of resistance 5 ohms, this one 2 ohms, right? And then this one 1 ohm, 1 ohm. Please, what happened with respect or with regard to the voltmeter shouldn't be a problem to you. You have your voltmeter, good one in the lab, so you can make use of it and you get your result. Now, from this end of this resistance box, another wire, which is wire 4, I guess so, is run into this standard resistor. And then the fifth wire will be run from the standard resistor to the positive terminal of the cell. So let us see how we achieve this connection. First, I'm going to start with the cell. This is our cell. This is our cell. So I would get my connecting wire. The first connecting wire from the negative end of the cell. So where do we have our negative end? This is positive. You can see that. Down here is negative. So this negative end, even my masking tape, they are all worn out. And I just got to run this quickly as fast as I can, at least to demonstrate it for you guys. So the negative terminal from the negative terminal of the battery, a wire is run. Look at the wire, and it moves to the negative terminal of the ammeter. So this is our ammeter. We'll be using that of 3 ampere. You can see your ammeter. This is the negative terminal, black cap. The red caps represent positive terminal. This is measuring up to 3 ampere. Look at it. Why this one is measuring up to 5 ampere. So for the experiment we're about to run, I am going to connect to this one measuring 3 ampere. Are you following, right? This one measuring 3 ampere. Because the current will not be more than it. The total current in the circuit wouldn't be more than that. So look at the scale. The lower scale measures up to 3 ampere. The upper scale measures up to 5 ampere. If you connect to this, you'll be using the upper scale. If you connect to this 3 ampere, you'll be using the lower scale. Like I said, in your laboratory, well, I guess you should be using this lower scale because the current wouldn't be up to 3 ampere even. I don't think so. It won't be up to 3 ampere. So from the negative terminal to the negative terminal. So this is what I have. The black cap is the negative terminal of the ammeter. So I have loosened this negative cap. I think it has one opening. So I'll pass my wire through it. Let's see. Good. The wire has gone through. And then I will screw. I'm screwing now. Remember the connection, negative to negative. In the circuit, there are only 2 components that have defined terminals. One of the components is the battery. The other is the ammeter. And just like I said, if you're connecting a wire from the negative terminal of the battery, it will run into the negative terminal of the ammeter. So let me even indicate in the ammeter, this will be negative, automatically making it to be positive. The other components do not have positive or negative. They don't. So if I run the wire from the positive of this ammeter this way to the key, it means that this end of the key will be positive also. And then from here will be negative in that way, okay? These are the only 2 components that have terminals. Negative of the cell to negative of the ammeter. So the next wire will move from positive of the ammeter into the key. Positive of the ammeter into what? The key. So let us do that. I'll get another wire. I have my connecting wires. There are about 5 connecting wires we need for this experiment. So look at the next one. From positive terminal of the ammeter. So I'm going to fix this. The ammeter has an opening, unlike the voltmeter that you have to turn wires around. So you fix it through the opening. All right, it has gone in. And then I will screw. Ensure tight connection. This is a precaution to ensure that you get accurate results. Okay? So you ensure tight connection before taking your reading. And this is actually to ensure that the pointer device does not lag. Let not be doing all this thing, back and front shaking. Okay, so we've done this. The next, remember, from the positive terminal of the ammeter, look at it, to the key. So I'll get my key. This is my key. I've told you that key does not have positive or negative. I'll remove this, tapping point. Then I will connect this wire to the negative. Is it negative? I'll connect this wire to this end of the key. I can't say the key does not have positive or negative. Now, this key, the screw here turns this way to tie. It turns this way to tie. Look at it. Something like this. Okay? Therefore, if I'm connecting the wire, I'm going to roll the wire this way. So that by the time, I'll roll it this way. So that by the time I am screwing this screw, I'm tying it, the wire will not be losing. So I will go this way. Observe that you are learning how to do the connection of this circuit. After that, I'll tell you the results that we had obtained earlier. Okay, so we've done this. I've tied the wire to the key. Then back again to the diagram. From the second terminal, the second end of the key, you run a wire into this resistance box. Like I said, we are going to be making use of this standard resistor. Yeah, I'm going to make use of it. In the instruction, we were not told the value of this standard resistor. This guy. It is either your examiner tells you a particular value you are going to use, or they won't even use this standard resistor at all, this one. But you'll be provided with the resistance box, which contains several resistors. If you pull up the cap of one of them, the resistor, that resistance box will become active for that particular resistor. So you'll be shown how to make use of that in your laboratory. It's very simple, nothing is there. I think electricity experiments is the simplest of all the experiments you've run so far. Okay, so we move. From this end, we run a wire to this resistor. I am going to use this resistor to be 1 ohm so that we can be running this directly and getting the value. But remember, the first row, you are meant to take the reading of the current when there is no resistor in the circuit. That's why I have 0.0, which means for the first reading, I will not make use of any resistor. I will not make use of any resistor. I'll just go straight with my connection. Follow along as I show you that. I'm trying to get wires ready. Trying to join some so that, all right. So assuming, as expected in the first case, there is no resistor there, it means that I'll be running this wire from the key directly to the cell. I don't want to make use of this standard resistance. It's not necessary. But if you are given the value, I'm saying this because in the instruction, they didn't give us the value of this standard resistor to use. So it's likely they might not make use of this. But if they do, they will give you the value of this standard resistor. It could be 1 ohms, 2 ohms, or whatever that they want you to use throughout the experiment. So this goes this way. Or maybe let me use 1 ohms resistance here as a standard. So this wire will run directly to that 1 ohms resistance. Look at 1 ohms resistor value here. Let's assume that's the standard. That's the standard resistor. So from the second end of our key, look at it. From the second end of our key, you tie this, and then you screw. Ensure tight connection. If a key is not provided, because sometimes they might not provide you with a key. If it is not, then these two wires, look at 2 of them, can be joined directly. You can always join and remove. If you remove, you open. If you join, you close. Okay? So whatever you see there, fine. Now, this wire from the second end of the key will be connected to this standard resistor. What we are trying to do now is to get the current when you have 0.0 ohms resistance value in this resistance box. So the first connection, you are not making use of this. You are not. So this goes straight to the standard resistor. If you are giving this standard resistor, like I said, fine. I'm trying to run the experiment in such a way that we assume that we are giving it. But in the instruction, the value was not given. That's the problem. But don't worry. In your laboratory, the value will be given to you if you are to make use of that standard resistor. You see that it's given, or they will just give you any resistor like that. So you don't worry about that. They will give you the guideline of what to do. All right, so I've connected this. The next one will now go from the second end of the resistor. You can say it's a wire from this key directly to this standard resistor, and then another wire from this standard resistor directly to the positive terminal of the cell. So this is the second end of the resistor. You can see that. I'm going to fix up this wire there. This thing screws this way. So I'm going to fix my wire to move that way as well too. Circuit connection, I've actually released a wonderful video lesson on it. So this thing I'm just trying to do is just to satisfy the curiosity of some persons, the anxiety of having this cell set up for them, this particular one. It's not really difficult. If you are taking that video lesson on experiment E2, although the connection there for that guy is parallel, but it's still the same principle you use. Trying to tie this, good. So from this second end of the resistor, the standard resistor, you have to connect this to the positive end of the battery. And this is the positive end of the battery. You've seen the circuit already. But for those of you in Unizik, you have the circuit there in your manual. So this is not new to you. All right, so that's it, something like this. So what if the S is a constant wire? Good. If it's a constant wire, no problem. That's what I'm saying. A constant wire is still the same as using a particular resistor. Are you following, right? So it doesn't matter. Whatever given to you, if it is a constant wire, they just give you a wire to fix that. That wire has resistance value. And the instruction did not tell you to determine it. So you have no problem there. Anything could have been given to you. Anything that has resistance could have been given to you here. So like I say, whatever they provide for you as the standard resistor, connect it there. Connect it where this 1 ohms resistor has been connected. Are you following, right? Simon Nnam, you asked the question. So take note of that. Remember, in this first connection, I did not include this resistance box. I didn't. This variable resistor, I didn't include it. Reason, we are trying to see what will be the current when there is no defined resistor in the circuit, which is for this guy, not this standard resistance, okay? For this one, when it is not included. So let us see what the reading is going to be. The instruction said, let me check the instruction there, said measure and record the EMF of the cell provided, which you have done, 2.9 volts. Then instruction number 2, connect the circuit as shown in figure E6 with R equal to 0 ohms, close the key and close the key, read and record the ammeter reading. Good. So we have done the connection with resistance of 0 ohms, this guy, which is why I didn't include any resistor here. Read and record the current. So let us see. To read and record the current, we have to close the key. We have to close the key. So I'm trying to adjust this for you to see. This is the key. So I will close it here. If you close it, as I'm closing it, look at fixing this, tapping points. It's expected that the circuit is complete. This ammeter is meant to read. But you see that the needle did not move. What could be the reason? Likely from here, likely from this part. You can see that the terminals of the cell, they were not fixed. My masking tape is weak, so I am going to use my hand. There is nothing there. In your laboratory, all these things will be provided. Support me very well. Provide all of this material always. So you watch. I'm trying to just fix that straight on. Now watch that the current, the needle or the pointer of the ammeter moved. Let me remove the terminal of the cell again. Watch my hand. As you're watching my hand, be watching the needle of the ammeter. You see, the pointer has gone back. It has gone back. So, we want to find out what's going to be the reading of the current with 0.0 ohms resistance. So, let's complete the circuit by closing or tapping this terminal. Look at what my fingers are doing here, my hand. You won't have this problem in your laboratory because you have a good masking tape that you could have masked this battery, these wires to this battery. Or you could be provided with battery casing, and that is the best to be used. Yes, your school is meant to provide battery casing for you on this. What I'm just trying to do is to demonstrate this experiment for you. Now you see that the ammeter moved. And what is the reading of the ammeter here? The pointer is between 0 and 1 ampere. Not up to 1 ampere, but each of the line in this ammeter is 0.1. Let me explain something to you. From this thick line 0, I'm going to shift this close. Let's see if you can see it clearly. From this line 0 to this 1, there are 10 small lines there. So since each of these current is 1 ampere difference, and between it is just like having 1 unit. Between it, you have 10 small lines. So each line will be 1 divided by 10. Each of this line is reading 0.1 ampere, 0.1 ampere. So you need to get to know this so that you know what the value of your current is. All right, I'm closing. Good. So you notice that this is around 0.8. 0.8. You can watch it. 0.8. So will you make this live a video for someone to watch later? Yes. At the end of this class, a copy of this live video will be made available. So with 0.0 ohms resistance, that is to say when there is no defined resistor in the circuit, apart from the standard resistance, which could be anything given to you. Like somebody asks, what if you are given a constant wire? Fine. You have no business with knowing the value of that standard resistor. Could be anything. Although here I use 1 ohms, but it's not compulsory that a value must be given to you. But the resistance box, that variable resistor, for this first experiment, you have to get the reading. That resistor, you shouldn't have any value there, which means that all the cap of the resistance box will be closed. You'll see that resistance box when you start your practical from today. All right, 0.8 ohms. Let's remove. So all you have to do is to go and record that, okay, for R, this R, 0.0, meaning there is no resistance activated in the resistance box. The current we obtained was 0.8, so you record 0.8. And of course, you can evaluate inverse of current. Inverse of current means 1 over the value of current you obtained here. I will advise, get your current completely first, and then use calculator to evaluate inverse of current, okay? To get inverse of current is simply 1 over what you obtained in the current. And let me press it for you. 1 divided by 0.8. And then you have 1.25. 1.25. So you can see for the first experiment, the inverse of the current is 1.25. But like I said, 1.25. Like I said, please obtain all the current first before you proceed to get the inverse. It will be faster for you in that case. Instead of getting this, evaluating the inverse, you get this. It's going to waste your time. All right, we are done with this guy. Let's move on to the next instruction. In the next instruction, what were we asked to do? That is instruction number 4. Repeat the procedure for R equal to 1, 2, 3, 4, 5, and 6 ohms respectively. Repeat the procedure for R equal to 1, equal to 2, equal to 3, equal to 4, equal to 5, equal to 6 ohms respectively. So we are meant to do for the next experiment 1 ohms. But sadly, I do not have another 1 ohms resistance for me to use in this second connection. But I have 2 ohms here, and that's good. So look at what I'm going to do. I will jump to this one. Your variable resistor in the lab, when they give it to you, it contains all this value already. So like I said, do not bother yourself. Enter there, you see all the complete equipment. By the time you guys support this channel, support GMAS 41 fully, I would continue to provide the equipment as much as possible. It's not easy, you know, on me. These are the ones I got sometimes past. So we move on. I am going to connect 2 ohms resistor now. So in your resistance box, all you have to do is to go and pull off the cap of 2 ohms resistor in that resistance box, because the resistance box contains all these resistors whose value they gave to you to use for this experiment. So let us check for these 2 ohms. And how do I do that? I'll go back to my circuit. The wire from the key, from the second terminal of the key, you will connect it to a 2 ohms resistance, a 2 ohms resistor. Then from the other end of the resistor, you connect a wire to the standard resistor so that this and this will be in series. Does that make sense? So what we are just trying to do is, in this circuit, look at this circuit that is very scattered there. Remember, at this point, you have your battery, your cell, something like this. Good. But the masking tape is not holding it. That's why the thing is off. And once you take your reading, you are meant to remove the tapping, this tapping key. You are meant to remove it so that the circuit will now be an open circuit in order for your battery not to discharge. But in this case that I am using my hand to connect, to hold the wires to the battery, even if I have this key closed, there is no problem, because with this wire disconnected from the battery, the circuit is no longer complete, and this is an open circuit. However, in your laboratory, I know for sure you are meant to fix these wires to this battery, whereas you'll be removing this tapping key. And that is what I'm going to do. Having done the first experiment, I will remove this tapping key. I'm assuming that my wire is connected, because as in my wire is connected to the cell, to the battery, because that's the right thing that is meant to be. All right. So with this, what I am going to do now, I'll go back to my key. Look at the key. This terminal of the key that was directly connected to your constant resistor, to your standard resistor. I'll go back there and then draw a wire from it into a 2 ohms resistance. This is supposed to be a 1 ohms resistor, but I don't have 1 ohm to use now since I'm using that 1 ohm as a standard resistor here. So I want to make use of 2 ohms. Let's get a reading of this guy. So I'll connect a wire from the key to 2 ohms resistor. Watch as I do that. This is going to be something like this. I'm going to disconnect this. I'm going to disconnect this because the wire is meant to be connected to the resistance box with our 2 ohms resistance activated. All right. Your resistance box contains all these resistors. So you are not even going to make use of all these single resistor. They'll give you a resistance box. In Physics 102 under electricity, I had shown what your resistance box looks like. All right, then from the second end, I am going to connect another wire. Mind you, this is the only reading we are going to carry out. And then I will show you something, I will tell you something rather, what happens as the resistance value is increasing. Remember, when you are fixing the second resistor to the standard resistor, you are increasing the value of the resistance in the circuit because these 2 resistors are connected in series. You saw that clearly from your circuit diagram. Let me show you once again. The resistance box, whatever value you activate from there, is connected in series with the standard resistor. I know when resistors are connected in series, the resistance value will increase. Resistors connected in series, the resistance value increases. And what will now be the effect on current? The value of current will decrease following Ohm's law. So the fact that I have activated 2 ohms resistance being connected to our standard resistance, and I'm using 1 ohms as the standard resistor, your lab technicians may not tell you the value of this standard resistor. In fact, in the instruction it was not given. Whatever it is not your business. What I'm trying to say is that whatever value of resistance you activate in the resistance box will be added to this standard resistor to increase the value of the resistance in the circuit. And when resistance in the circuit increases, what will be the effect on current? Current will decrease because according to Ohm's law, current and resistor or resistance, they are inversely proportional. So I am connecting these 2 ohms resistance activated in this resistance box now directly to our standard resistor. So look at the 2 ohms resistor activated in the resistance box. Supposedly, you can see a wire from it straight. Look at the wire from it straight to our standard resistor. Remember, I'm using 1 ohms as a standard resistor. Like I said, you may not know the value. Somebody had asked, what if they give a constant wire? That is likely what might happen here. And that is why from the beginning I was saying that the standard resistor might not even be necessary. It might just give you something there, or you run it straight on. All the same, whatever you see there, follow the principle of what you are learning here. Like I've always said, this is a full-blown online school to guide you and give you full principle, not to make you cram some unnecessary things. No, understand the principle and that's all. Now, take note that the standard resistor, from the other end of it, the wire is connected to the positive terminal of the cell. So, look at it. This end of this standard resistor, the standard resistor is already in series with these 2 ohms resistance. You can see that. So, the wire from here will be connected to the positive terminal of the battery. Look at it. So, I'm going to use my hand to hold this. This is very, very sad and embarrassing, Abi. You could say so. Because this is embarrassing. He could have used masking tape. I have masking tape here, but the tape is not masking. The tape is not masking, no. Okay, let's see what happens. But I can use my hand. This is how it's meant to go. But the masking tape is weak already. That's what I'm trying to say. Why this one also? From the other end. Let's see. This is stressing me. Going to use my fingers to hold them straight. Don't have time. I want to believe that you understand the principles already. So something like this. Now you notice that the pointer of the ammeter is not moving. Why? Because the circuit is in open state. This is an open circuit yet. Why did I say it is an open circuit? Let me see if I can use one hand to hold this battery. See how I'm punishing myself here, stressing myself because of you friends. Support this channel. I'll really appreciate. Join us on the platinum or diamond level. Now the pointer is not moving. Why? Because this circuit is not complete yet. Look at this part. There is a bridge here. The tapping key has not been completed, has not been closed. So look at my tapping key. I'll close it now. And as I'm closing, watch what is going to happen. Remember, from what I explained here, I have activated 2 ohms resistor. 2 ohms resistor in this resistance box. Connected to this constant resistance in series. The total resistance will now increase because you are adding this to this, if it is theoretical, right? Which means the current you are going to get in this circuit, in this second case, will be less than the initial current we obtained of 0.8. When we got 0.8, the resistance there was 0. Here, I have activated 2 ohms resistance. So the current I will get here will be less than this 0.8. Let's watch and see. And this is because current and resistance, they are inversely proportional. I am closing my tapping key and watch. Be watching the ammeter. The needle will now move. I've closed the key. The circuit is complete now. Watch what we obtained. The needle is pointing here. You can see it here. You can see it here. And that is exactly 0.5. That is exactly 0.5. Trying to see if I can adjust it a bit for you to see. Good. 0.5. Make sure you avoid error due to parallax. That is another precaution you take to ensure accurate result. You look straight, perpendicular to this measuring instrument. You don't look from the side here or from this side. No. I can't show my face now. I could have shown you directly. You look, your eye should be fixed directly at this needle, perpendicular this way. Are you following, right? You know that already. If I remove one of the end of this key now, watch the needle of the ammeter, it will return back because that will now be an open state. You see what happened? The circuit is now open. It's no longer complete. It's no longer closed. Now let me put back the terminal and you'll see the needle still moved back to that 0.5 ampere. Do you see that it agreed with what I explained? With 2 ohms resistance, the current we obtained, as you are seeing here, is 0.5, which is less than the first one we obtained when the resistance was 0 ohms. So this actually follows the theory of this experiment. So what do? Now I have taken my reading. I will open the key. Now watch. Because I am meant to open this key, remove it. You see that as I removed it, the pointer went back because current is no longer flowing. This is an open circuit now. Record your 0.5. So you watch 0.5. If you carry out the experiment, the current will be decreasing because based on what you were told to do in the instruction, you are meant to be increasing the resistance value. You can see the instruction. You are meant to be increasing the resistance value. Repeat the procedure. Instruction number 4. Repeat the procedure for R equal to 1, equal to 2, equal to 3, equal to 4, equal to 5. I jumped 1 because I didn't have 1 ohm resistance to have used now. I made use of 2. All right. Now, I don't think I have 3 ohms resistance, so I'm going to jump to 5. And if I work for this 5 ohms resistance, you will find out that the current value we are going to get will still be less than this one we obtained for 2 ohms. Why? Because I've increased the resistance to 5 ohms. This resistance box, 5 ohms of it will now be activated. You go to the resistance box, pull off the 5 ohms cap, and that activates the 5 ohms resistance of the resistance box. You know, that 5 ohms will now be added to this standard resistor. The resistance here, it's the value you have there. These 5 ohms will be added to it, thereby skyrocketing, increasing the value of the total resistance of the cell. We do all this calculation in Physics 102, you know, where you do resistors in series and resistors in parallel. This is series connection. So for any of the experiments you repeat, the value of the total resistance will increase, the effective resistance will increase, thereby reducing the current. So that is what you expect to observe as you are running this experiment throughout this week. All right, let me do the last one for 5 ohms. Now for 5 ohms resistor, what am I going to do? I will go to where I made use of 2 ohms initially. Look at it. This is my 2 ohms. To activate 5 ohms resistance, I will remove this and then fix 5 ohms. This is 2 ohms, you can see. I'll remove it and fix 5 ohms. But like I said, you won't go through all this stress that GMAT 41 is going through for you. You won't, because the resistance box given to you already have all those resistors. There's just to pull off the cap. That's it. It's just to pull off the cap. You know how to activate it. Thinking that you pull or you fix the cap. But I guess it's to pull. All right, now I have removed this. I've disconnected. I'll bring my 5 ohms resistance. Look at it. So let's fix up. Like I said, once again, you will not be doing all this, remove this resistance, you know, and then you tie again. You won't be doing that because your resistance box, to activate it, like I said, is just to pull the cap of the particular resistor you want to, or the particular resistance value you want to activate. So the other end of it, connect a wire to it and then screw. Like I said, make sure you ensure tight connection. All right, this thing is trying to disturb me here. Okay, so I screw. Remember, I have revealed the secrets to you already, that the way you wrap your wire, you fix your wire, should be in the direction that you screw. Otherwise, if you are screwing, if you fix your wire against the tightening direction, if you fix your wire against the tightening, direction, when you are tightening the stuff, it will be losing, and that will waste your time in the laboratory. But anyway, like I say, you wouldn't have all those challenges. Now you can see 5 ohms resistance activated in series. You can see straight line, a straight wire drawn in series to our standard resistor. For the standard resistor, I'm using a constant value of 1 ohms. Whatever is given to you as your standard resistor, connect it here. Are you following, right? That's why you don't need to copy these values we are getting from here directly. It's not advisable. Work on it in your lab. You can do it. Okay, so what do we do? Remember that this is connected to the standard resistor, and then from the other end of the standard resistor, you connect to the positive terminal of the battery. That is what the diagram showed you. Once again, watch. If you activate any particular resistance value from the resistance box, you see a straight wire connected in series to this standard resistor. From the other end of the standard resistor, you connect to the positive terminal. But all this connection would have been done already. The first connection you would do, everything will be intact for you in the laboratory. So don't bother yourself. You won't stress at all. This experiment is very sweet and simple. You can't compare it anywhere at all with your lens, convex lens experiment, triangular prism, or even rectangular prism. Okay, back to our cell part. Like I said, this cell, the wires are meant to have been taped. But my masking tape, like I said, is not taping. I mean, it's not masking. So I am holding the cell, the wires to the terminals of the cell. You notice that the needle, the pointer of the ammeter is not moving. Why? Because the circuit is in open state. This is an open circuit. To close it, you have to fix this tapping key. Now, as I am fixing this tapping key, please watch the pointer of the ammeter. It's going to move. And the value of the current we'll get here will be less than the 0.5 we obtained for 2 ohms resistance, because we are using 5 ohms resistance now. Let's prove it and see. I'm closing the key now, watch. And then be watching the needle of the ammeter. I've closed the key. Observe, this is where the needle of the ammeter is pointing now. And if you watch, it's around 0.3. 0.3, look at it. 0.3. So, go straight on and record 0.3. So this is what you are meant to do. In fact, this experiment, if you are running it, one thing about it is the value seems to be reducing by 0.1, 0.1, 0.1. So that is one key secret. Yes. And I want to tell you this. Why not trying to tell you to go manipulate or whatever? But just because of time factor, if you feel that you are choked with time, after running the first, the second experiment, watch the pattern. Take the difference. Find out how the thing is reducing. And like I said, from the experiment and experience from it already, I've observed that this experiment, and mostly many electricity experiments, whenever you are doing all this current stuff or voltage stuff, their values reduce or increase by either 0.1, 0.2, something within that range, 0.1, 0.2. So let me tell you something. After running this first guy, this one I could have just subtracted 0.1 from 0.8. I can decide to record 0.7 for this 1 ohms resistance, or even 0.6. Because like I said, their difference is within the range of 0.1, 0.2 difference. And you can do that confidently if you are choked with time. You can do that confidently. Julia Ujungwa, you are welcome. I hope you're doing fine. Welcome to join this class. All right. If I had run for 6 ohms resistance now, the current might be around 0.2 or 0.1. Just subtract 0.1 from this 0.3 or subtract 0.2 from this 0.3. The choice is yours. You should use your IQ in this case. Some of them you can subtract 0.1 to get the other one. Others you can subtract 0.2 to get the other one. So you have this variation of differences. All right, guys, I hope you've learned something wonderful from how you are meant to carry out this experiment. Like I said, once you are done obtaining all these values, you can now obtain the inverse. And how do you get the inverse? 1 over the value of the current you obtained here. For example, this 1.25, we obtained it from dividing 1 by 0.8. You know how to get the inverse of something. Okay, let us get this one. 1 over the value of current, inverse of current. The value of current is 0.5. So 1 over 0.5, let's see what we are going to get. 1 divided by 0.5. This gives 2, which means that this is going to be 2. I'll record 2. Let's check for this. 1 divided by 0.3. 1 over 0.3. So this gave 3.333. We're going to pick 3.33, 2 decimals, 2 decimal, 3.33. This one should be 2.00. Your ammeter reading should be in 1 decimal. The inverse should be in 2 decimals. All right, dear friends, if Naya Benedict, you're welcome to join this class. We've already run this experiment, okay, what you're meant to do, and I hope you enjoyed it. Remember your precautions. Ensure tight connection, all right? Remove the tapping key. That's, remove the tapping key after taking reading. This is to ensure that the cell does not discharge, okay? Then avoid error due to parallax. How do you avoid error due to parallax? Because if you are quoting your precautions, if you are stating it, you have to tell us how you carry, as in how you actually carried out that precaution, and for what reason, if need be. Okay, so you want to take note of that. I removed the tapping key, or I kept the circuit open after taking reading, in order to prevent the cell from discharging. I avoided error due to parallax by looking perpendicular to the pointer of the ammeter. I ensured tight connections in order to prevent lagging. Are you following, right? Lagging of the pointer of the ammeter. Because if the connection is not tight, this pointer, once you think you want to take the reading, it will be moving this way. Okay, a lagging stuff. All right, guys. In part 2, we are going to see the follow-up questions. See, let me tell you something, dear friends. Let me tell you something. You guys know GMAT 41 already, if you've been following my works, that I believe in training noble minds. Minds that believe, right, in what they know. Issue of plotting the graph for you here, I don't have that time. I wouldn't do it for you. I wouldn't do it for you. Part 2, we just go to the follow-up questions. The follow-up questions, there were some things they asked you to calculate. Now, after you have taken your reading, look at the instruction. From here, I can see you are told to determine the slope S and the intercept on the vertical. Okay, let's see what they say you should plot first. So that I will tell you the shape of the graph. Evaluate I inverse and tabulate your reading. Okay, you have known how to tabulate your reading. Plot a graph of R against inverse of I. Plot a graph of R against inverse of I, starting both axes from the origin. I've already taught you, how to plot graphs. I have several works on it. Whether the graph is a normal graph or a graph where the values are too close. And when values are too close, you need to stretch the graph. I've taught you graph stretching principle from last semester already, a few months ago. And I want to believe that by now, noble minds, those that are working hard, that knows, what they are doing. It's not every time you wait for someone to finish all works for you. That is not a good way of learning, dear friends. I love you guys very much, and I want the best for you. By now, all of you should know how to plot whatever kind of graph you're exposed to. Now here we are plotting this column, R, against this column. This guy, you don't have problems there. The unit you are going to use there should just be 1 unit. Can say 2cm equal to 1 unit, okay, as the case might be, or 2cm equal to 2 units, as the case might be. This is a uniform reading. But look at this one. The values will be clustered. The values will be close together. This I inverse. You are plotting this on the vertical and this on the horizontal. So let me show you a sketch of what the graph would look like. Looking at the values, the resistance values are increasing from 0 to 6. The inverse of current is also what? Increasing, if you see it. Okay? So both of them are increasing. The relationship is the same. Increase, increase. So the graph is going to be a direct proportional graph. It should be something of this kind. Let me show it under here. Vertical, horizontal, R in ohms, and then I inverse. The unit to be inverse of ampere. Something of this kind. Okay? Like I said, here you don't have problem in your units. The unit, whatever centimeter you are using, whatever centimeter should go with either 1 unit, or 2 units. The choice is yours. Or 2 units. You see that you write 1 unit, or you can write 1 ohm, like saying 2 centimeter equal to 1 unit, or 2 centimeter equal to 1 ohms, because this axis is in ohms. So either you write units or ohms. In fact, let me write the grammar here. Whatever unit, whatever centimeter rather. You know the centimeter is your choice. Whatever cm to either 1 unit or 1 ohms, or 2 units or 2 ohms. Then if you come here, see this axis, you will need to stretch this axis. You need to stretch. You need to stretch the I inverse axis. I told you the reason. These values you have here, they are clustered. They are quite close together. Yeah, somehow. They are quite close, I guess. So you might have to stretch this horizontal axis if care is not taken. But whatever you get in the laboratory, let it guide you. I'm just telling you, you might have to stretch this. So you work on how to stretch graph. I have a video lesson on it. You can go to GMAT 41's playlist, Physics 107/Physics 108. I have a particular video. I taught the principle of graph stretching, so you know how to handle this other axis. Meanwhile, I think experiment E2 on electricity is still there on the channel. On this channel, Phase 107/Phase 108 playlist. If you go there, the first 3 sets of videos there. The 3rd lecture video is on graph work of that experiment E2. I think one of the axes I stretched the graph, so you can still learn from the principle of graph stretching from there. Okay, so the graph will go this way. The graph will go this way. Let me see the theorem guiding this. It's going to be a positive graph, something like this, because both of them are increasing. Both of them have the same pattern. All right, so I'm trying to check whether this should have intercept also. All right, it defined this thing was not given. It follows Ohm's law. So you are also told to get the intercept. So the graph would have to go this way. This should be the shape of the graph, something of this kind. And then you now read your intercept from whatever you get it from the origin to this part. This height is your intercept. And they said you should use what to represent the intercepts? Evaluate the intercepts. C should be used to represent the intercepts. So from here, the origin to this is 0,0 whatever. From here to this is your intercept, C. Then your slope, I want to believe all of us knows how to get our slope by now. This is how you evaluate your slope. Change in R all over change in I inverse. So from here you get your slope. Slope S is equal to change in R over change in I inverse. So you get the 2 values you need to calculate the slope. So that is that based on the instruction. There is no big deal here. It's a very straightforward stuff. Like I said, the works you have done already on your practicals, they are far tougher than this one. Now, let us conclude in this. I think the precautions I've been telling you about it. Then question number 3. A parallel combination of 3 ohms and 6 ohms resistors is connected in series. Let me see if I can hold this against this place and then read. Yeah, a parallel combination of 3 ohms and 6 ohms resistors is connected in series. It's connected in series with a resistor of 5 ohms and a battery of internal resistance 1 ohm. Calculates the effective resistance in the circuit. Then we have another question, question number 4. An electric bell takes a current of 0.2 ampere from a battery of 2 dry cells connected in series. Each has an EMF of 1.5 volts and an internal resistance of 1.0 ohms. Calculates A or I, the resistance of the bell, II. What amount of current will be delivered to the bell? If the cells were arranged in parallel? Good. That's the question. So the solution to this will come in part 2. The solution to this will come in part 2. And I might go live in part 2. Or let me see. Maybe I might just I'll still come live. No time. Let me just be quick. I've already solved the questions. Okay. So just to give you the interpretation. And so I think we are done with what you are meant to know. Let me just show you that I've actually done the calculations of this stuff, of the questions. You can see that with neat diagrams, but I'm going to go live so that you can have the solutions. And if you have any question, you can ask. These are the solutions to that question, all right? So stay put. We are done with the part 1. I'm going to activate another class right away for part 2, where we'll now do the follow-up calculations, okay? Thank you for connecting to the class, and I hope to see you in the next, part 2. If you have not subscribed to this channel yet, make sure you turn on the notification bell, subscribe, turn on the notification bell, select all, because anytime I create a class like this, you need to be notified. You need to be notified. And if you don't turn on the notification bell, you won't be notified. Let me show my face now. Let me show my face. I see my face. I don't know if I'm actually showing. I think let me adjust this. So you see the face of the GMAT this morning. All right. Get prepared as we move on to part 2. Ugochukwu Mose, thank you. Faith Ubana, thank you. Thank you guys for connecting. Let's go to part 2. For our dear students already, you have the solution through our Telegram channel, I guess. I think I dropped it. Is it early this morning or midnight or so? I don't know. But let me make it public to everyone else. Onyinye Julia, thank you also for appreciating us. So let's go straight to part 2, please. You receive the notification once I create the class.